today's topic, I kind of apologize in advance. This is going to be like really, really heavy on memorization. And I don't really have any better way to kind of do it, except that you're really going to have to memorize a lot of these kinds of rules and get a lot of practice at applying them. But I think after you do this, like, you do like 5 of these problems, you'll start to get a feel for it, I think. But yeah. So if you remember so far, like, kind of the main tool that we've built up so far is just truth tables, right? If you want to, prove, let's say you want to prove 2 different things are logically equivalent, the kind of main approach that we have is, draw a truth table for them and see if they have the same truth values for all the, all the possibilities. So what we're going to try to do now is build up some other methods for doing things like proving logical equivalence. Basically, the idea is if you have a whole bunch of kind of known logical equivalences that you know are true, you can sometimes use them to get other logical equivalences by just kind of applying them over and over. Okay, so let's kind of go through them a bit. So like I say, these are things that you're going to need to remember. You're also going to probably need to remember these names. And we'll see how to use these. I'll give you an example in a minute. But first, let's kind of just go through them and see if we understand them. So these first 2 laws, let me go zoom in. So they're called idempotence. P or P is logically equivalent to P. Right? I think that's pretty self-explanatory. P and P is the same as P as well. Okay. If you really wanted to, you could prove this with the truth table, but I think we kind of understand that. Commutativity, this is probably something I may have even accidentally just done it in class. Like, I mean, in the sense of, it's sort of a thing, it's kind of obvious, right? That P or Q is the same as Q or P. You can switch the order. P and Q is the same as Q and P. So, by the way, all of these words have some real kind of meaning in mathematics. So if these are the first time you've seen these words like idempotence or commutativity or associativity, distributivity, etc., you're going to see them a lot of times in your, well, if you're doing a math degree. Idempotence is kind of, it's kind of the idea that you apply, you kind of, if you have something and you do it twice, it's the same as doing it once. And you can see it's kind of P or P is the same as P. Actually, maybe I should say that all of these things are kind of, so these rules are going to be somewhat analogous to things you see in algebra, right? So commutativity, for example, is kind of like the fact that x plus y is the same as y plus x, or x times y is the same as y times x, right? And so you have a similar thing with and or, that you can switch the order. Okay. Then we've got associativity. So associativity, basically the idea is, so this is something to be, this is very important, that here we've got an or in both places, so it's P or Q. Well, here it's P or Q or R is the same as P or Q or R. You can move the brackets to either place, right? And the same with and, but you can't do this if there's an and an or. But that's the same thing as kind of like x plus y plus z is the same as x plus y plus z. And similar with multiplication. Right? But if I had a x times y plus z, you couldn't just move the brackets around, right? Okay, next one. I apologize that this is going to be a really boring lecture. Just kind of going through these things, but distributivity. So this is kind of, it kind of starts looking like at a place that looks the same as the associativity, except now we have a mixture of two different connectives. You have or and, which is kind of like multiplication and having a mixture of multiplication and addition, right? So if I had x times y plus z, so what you do with this is you take the x inside and you apply the multiplication to each of the inside things and you add them, right? So this is xy plus xz. Okay, and the logical, the logic works in the same way, these logical connectives. So if I take P or Q and R, what you can do is basically bring in the P or, into the bracket. So it becomes P. You apply the P or to the Q and to the R, and put an and between them. Right. One difference is that with logic, this works in the same way in both directions. Like if I change this or to an and this and to an or, the same thing works. Whereas with addition and multiplication, it doesn't work both ways, right? I can't do anything with this, x plus y z. I can't like factor it in or something. But yeah, you should think of distributivity like this. Is that okay? Any questions about that? By the way, all of these things, if you wanted to prove them, how would you do it? Truth table, yeah, exactly. So maybe some of these, maybe not the ones we've talked about so far, but some of the ones coming later, we've actually proved in class using truth tables, like these De Morgan's laws. But yeah, you could prove any of these with a truth table. Double negation, that's almost too obvious, right? If you take not P, it's the same as P. De Morgan's laws, we did one of them in class. So now I've scrolled down, we're up here. So if you take an or and you negate it, it gives you the negation of the and. So it's like, it gives you the, well, let me just say in words, not brackets P or Q is the same as not P and not Q. And then similar thing with and. So for the purposes of explaining the next few things, I'm going to let bold 1 be a tautology. So you could think of, remember tautology is always true. So for example, P or not P would be a tautology. P and not P is a contradiction, right? So we can just let 1 be any tautology and 0 be a contradiction. And then all of these things are pretty, I think, easy to see as well. So identity, so P or 0 is equivalent to P, right? Is that clear? So because if I take P or 0, if P is false, then P or a contradiction, or P or 0 is false. If P is true, then it becomes true, right? Actually, this is, when I'm talking about identity here, I mean, this is kind of also like algebra, right? If you think about or as being like a plus, it's kind of like saying P plus 0 is P. And the second one is kind of like P times 1 is P, in a sense. Now, yeah, you shouldn't turn everything into like algebra and try to understand it that way, because some of the things are different. But this is kind of what's going on in this identity thing. So P and a tautology is the same as P. Does this help to talk about the algebra stuff, or is it just more confusing? I don't know, but I'm just trying to say that these are things you've kind of seen before. It's just in a different context. Similar concepts, different, yeah. Okay, so yeah, these are now different than in algebra in some sense. So P or 1, if you think about that, P or a tautology is always true because the tautology is true, so it just becomes true no matter what. And P and 0 is true, or sorry, false. Then we've got these things like we've got basic, I wrote this on the board, this basic tautology, the basic contradiction. If you ever see one of these, you can always replace it by a 1 or a 0. The negation of a tautology is a contradiction, and vice versa. Yeah, so the things we've gone through so far, I guess I think if you look in the notes, so the things kind of above here, the notes, I think, calls those things or something like that the laws of logic. And then there's like a list below that, which is like, and these things are also useful as well. So that's kind of, that's these last few things they're not technically called the laws of logic, but they're also very, useful. So the first one is the contrapositive. I think we talked about that last time, that P implies Q is the same as not Q implies not P, right? So if you have an implication, you can take the contrapositive, and it gives you the same thing. We also did this one at some point with a truth table. So P implies Q is the same as not P or Q. We also did this one with a truth table, that P if and only if Q is the same as P implies Q and Q implies P. And these ones down here, which we're calling absorption, they kind of look weird, actually. But if you think about it, it's kind of clear why this is true. So if Q is true, and I look at this side, then this Q is going to be true. Then P or Q will also be true. So if Q is true, this side is true. If Q is false, then that Q is false, so it's already false. So it's kind of, if you think about it, it's clear that these things have the same truth value. Anyway, okay. So let's do an example of how to use these things to prove something. Okay. So what I want to prove is that. This is a kind of question you could see in an exam or on an assignment or something. Oh, by the way, does everyone know that there's an assignment now? So use, let's say, known equivalences, known logical equivalences, and laws of logic. So the question might say, it might be phrased in all kinds of ways, but basically you can use, you can probably always use these things, any of these things, to prove that P if and only if Q is logically equivalent to P and Q, or not P and not Q. In some sense, this is kind of evident because, the fact that this is true shouldn't surprise you, right? Because, P if and only if Q means they have the same truth value, right? Which is the same as saying P and Q are true, or not P and not Q are true. So this makes sense, but you still have to actually prove it. Okay, so the way I would suggest approaching these things, well, first of all, is to start on one side. And so start somewhere, apply a whole bunch of logical equivalences, and try to get to the other side. But one thing, a kind of tip is to, so if I start, let's say I start on this side with the if and only if. So most of these rules are about ands and ors and nots. So this kind of connects back to this question from before, what can we do with biconditionals and stuff? These are pretty much all about ands and ors and nots. So a kind of tip is to convert everything to and, or, and not, in the beginning. You maybe don't necessarily always have to do that, but it's kind of a good rule of thumb. So I'm going to start with this side, and I'm going to try to get it in terms of ands, ors, and nots first, and then I'm going to play with it, and hopefully we'll make it to this side by the end. Okay, so I start with P if and only if Q. So as a first step, what I'm going to do is I'm going to break it up because we know that a double implication or a biconditional is the same as two single implications, which I admit is not, this is not in terms of and or not yet, right? I've still got implications, but in some sense, we're getting a bit closer. So here, what I would write is, so for every step you do, this is important. For every step you do, you've got to write a reason. Like you've got to write some reason why you're allowed to do that. So here I'll write that this is a known LE. LE stands for logical equivalence. Yeah, this is basically because this is one of the standard things we know we've proven in class, and we know that it's true. Okay, like I said, my first goal is to get this in terms of ands and ors and nots. Does anyone have a suggestion for what to do next? Yep. Totally. Yep. Yeah. So for example, this one becomes exactly. Yeah. So that's great. So that's what we want to do. So so that one becomes not P or Q, and this one becomes not Q or P. Yeah, that's perfect. And this one I'll say, again, it's a known logical equivalence. I mean, in some sense, all of these things are known logical equivalences, but when they have a special name, we're going to want to use a special name. But anyway. Okay. Maybe it's not clear what to do next, but so what I see here is kind of, I mean, imagine this part as just being kind of one, statement by itself. I mean, it is one statement, but it looks complicated. But imagine this being like R, a statement R. Then this is just R and not Q or P. And if you think about it, we've got exactly the right setup for the distributivity law. I guess it's the second one because it's, something outside and with an or inside the brackets. And what we can do is bring that inside the brackets in some sense. Is that clear? So if I think of this whole thing as being one block, one statement, I can bring that statement inside. So this is going to give me a lot of brackets, I think. So, so what I want is not P or Q, and not Q, or not P or Q, and P. And this is by distributivity. Right? So it's kind of weird applying the distributivity to this complicated thing, but yeah, it kind of works. What next? Yeah. Yeah, on the inside, right? Yeah. So now I'm going to pull this thing inside and pull that thing inside. I guess the way that this distributivity is written, it's written with the brackets second and the thing first, but I don't think we don't need to worry about that. Like, I mean, technically what I'm doing here, I guess I'm applying commutativity. You could apply commutativity to switch these and then pull it in. But I think it's okay to just say distributivity also works from the right-hand side. That's okay. So yeah, let's distribute. So here I'll get not P and not Q, or something weird, which is not Q, or sorry, Q and not Q. For the first one, bringing that inside, applying it to there, applying it to there. gain, something weird, P and, or sorry, not P and P, or Q and P. So this is, so my reason for this is distributivity. But just to make it clear, you might want to say like times 2, because I applied it twice. So now I've got a bunch of contradictions in here, right? Yeah. So as my next step, what I'm going to do is I'm just going to replace them with zeros, like a bold 0. I don't know exactly how to draw that, but let's yeah, that's my bold 0. Or, oh, sorry, that's the wrong one. So it should be not P or not Q, or sorry, and not Q, or bold 0, or bold 0, or P and Q, or sorry, Q and P. And this is a known contradiction. Right? Because we know that, yeah, P and not P is a contradiction. So then I go back to these rules about contradictions and tautologies. And I think what I want now is the identity rule, the law or whatever. So if I have a P or a contradiction, it's the same as P. Right? So I can just get rid of I can just basically just rewrite this as the first part. So, and yeah, this is kind of a lot of steps, right? Which kind of sucks, but yeah, I think you don't want to do too much skipping steps because first of all, you might make a mistake, and second of all, maybe you might lose marks or something. I mean, I think the important thing is really to explain what you're doing, but yeah. Probably if you explain everything really well, you can do whatever you want, but yeah, the safest thing to do is to do loads and loads of steps like this. So this is the identity rule times 2 on each of these. Okay, and now I've actually pretty much got what I wanted. I was aiming for, so just to, I think I erased it. So to say what I was aiming for was, so the final thing I wanted was this or this, right? Which is practically what I've got, except things are all scrambled in the wrong order. But I can reorder everything, right? So I can just say, I can use commutativity to write this as P and Q, or not P and not Q. But I would say I'm kind of applying it, commutativity twice. So I apply it to switch the order of these, and then to switch the order of this one. This one was already in the right order, so it's fine. And yeah, and that completes the proof. Yeah. I think, so I can never really give a full answer to these questions because I know for sure that I'm not always going to be the one marking your work. So sometimes there'll be another instructor. Sometimes there'll be a TA. If they're looking for this step and you haven't done it, then yeah, I can't guarantee that they won't take away a little small mark, but like I do agree, this is just so obviously the same as this. But yeah, I would do it. If you want to be safe and make sure you get all the marks, I would do it. Any other questions? By the way, I think I've maybe last time was trying to, I'm not sure if I said this or not, but trying to sell this like I want to try to say that this is easier than doing truth tables and shorter. But I think in this example, if you did a truth table for this, it'd be much faster than what I just did. But But so sometimes this method of using known logical equivalences can be faster than a truth table. Sometimes it's slower, but you have to know how to do both because you might be asked to do one or the other. Okay, any questions? Okay, so this is kind of one example. If there's time later, I might do another example, but basically, all of them are sort of like this, right? Start on one side, turn it into ands and ors and nots, and just break things down until you get to the other side. I would suggest doing a lot of practice with this. There's a link on the Brightspace to old final exams. That's probably the best place to practice. So you'll be able to find lots of these questions there. And there's lots of examples in the notes as well. But yeah. So just like with truth tables, getting fast at doing these will also be a huge benefit for you. Okay. So let me tell you about arguments. So an argument, for the sake of this course, actually, let's rewind a second, okay? So sorry, there's something I wanted to mention just briefly. So remember in these things I said the first step is to turn everything into and, or, and not. In these logical, these laws of logic problems. I just wanted to just briefly mention that you can always do that. Well, so there's something in the notes about this. This is kind of a side comment. I wouldn't take this as being extremely important, but it's kind of, yeah. So you don't even necessarily have to write this down, but I'll continue back there. But yeah, so just a comment that everything really can we've kind of already seen that in some sense, right? Because P implies Q, we know is the same as not P or Q. And P if and only if Q, we know is the same as, and this is like this thing about doing two steps at once, right? You can always, so you can feel free to write this as not P or Q, and not Q or P, right? So that already tells you how to write these things in terms of ands and ors and nots. One little side comment just from the notes is actually technically, if you really, really wanted to, you could write everything in terms of just ands and nots with no ors. Now, I wouldn't recommend doing that because it'll just make your expressions much longer and more complicated, but you could if you really wanted to. Because if I take P or Q, and let's say I want to write this with no or, what I can do is apply De Morgan's laws, well, one of them, which tells me that this is the same as not P, and not Q. Right. And therefore, if you really wanted to, you could write everything in terms of ands and nots, or you could write everything in terms of ors and nots, because I know that P and Q, so this is De Morgan, is the same as not P or not Q. Right. Yeah, anyway, this is not necessarily going to be something you're going to use, but just a sort of comment. Okay. Any questions about that? Yeah?
I noticed whenever it's working around the double-lined arrows, is that like a rule of thumb?
Do you mean like kind of treating them like an equal sign and the thing is there's no like, I guess there's no kind of cancel, like there's no kind of dividing and, you know, minusing things, right? So there's no kind of way to kind of cancel things. So yeah, so in some sense, all of this does feel like what you do in algebra, except we aren't going to write an equation and then move things around. It's really going to be like you have you start somewhere, you do something, and then you keep going like that, rather than canceling things or anything like that. Yeah. Any other questions? Okay, let's get back to this. So an argument is a statement of the form P1 and P2 and ... up to Pn implies Q, where I guess all of these P1 up to Pn are statements and Q is a statement. So it's kind of like, it's a sort of thing like if this and this and this and this are true, then that is true. You know, if P1 is true and P2 is true and up to Pn is true, then Q is true. So in an argument we call P1 up to Pn premises and Q, Q is called the conclusion. So in other words, the kind of structure of an argument is, if the premises are true, then the conclusion is true. So, for example, I could take something like P implies, so I could take something where the premise is, so the first premise is P implies not Q. The second premise is not R implies P. The third premise is just Q. And my conclusion is not R. So this is like premise, 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 and then conclusion. So we often write these things as in sort of like a table kind of thing. So this is kind of ugly because we got all these crazy brackets and stuff. It's usually kind of cleaner to write this as, so we write an argument like this. So let's just look at it in this example. So I'll write my premises first. So P implies not Q, not R implies P, Q with a line, and therefore not R.
When did we start mentioning
I guess I usually have p's and q's all the time, right? But yeah, it's just a yeah. I would be careful not to call it a variable too often, but yeah, it's a third statement. But yeah, we do treat it like a variable anyway. But yeah, it's just a third statement. Yeah, yeah. I could have any number of statements here. Just well, at some point I'll run out of letters of the alphabet, but yeah, you could have all kinds of statements. Any other questions? You can kind of think of this like as a kind of sentence, right? It's like P implies not Q, not R implies P. Q, kind of meaning Q is true, therefore not R is true. Kind of, these are kind of puzzle pieces. It's like, putting this together tells me that not R is true. But in this particular example, does it? I mean, if I put these things together, like, does it imply that not R is true? Or is this complete nonsense? So that's one thing you're going to have to be able to check. So one type of question you'll see is you're given an argument written in this form with something, line by line by line, therefore conclusion. And you have to say, is this valid or invalid? Like, is this just nonsense, or is this really an argument? Is this a true argument? So it is valid if, I guess it's valid if an argument is valid if, I guess if it is a tautology, so if it really is true, and it's invalid otherwise. So basically it's invalid if it could be false. If there's some way of choosing my P's and Q's and R's such that it evaluates to false. So in this case, this is not valid. This is invalid. And we can prove that. So how would I go about proving that this is invalid? So in other words, I want to prove that there's a choice for P, Q, and R such that this implication is false. So where would I start? Yep.
Can you argue like on the whole statement itself? Like if that's supposed to be then Q has to be, if Q is true, then not Q is false, then P has to be false as well for that to be true. So P is false, so not R is false, but there not R is true.
I think you've got all the pieces there. Yeah. I think you've got everything there. Let's kind of try to, I'll try to give you like a more systematic way that can work every time, but yeah, that's going to work. I mean, like kind of the big picture is to make this false, I have to make the conclusion false and the premise is true. Right? And that's what you were doing in this argument. You started with Q to make that one true, which makes sense, and then you kind of worked out the rest of them. So to show it's invalid, we want the conclusion to be false and all the premises to be true. Like every single premise to be true. So maybe so the way you did is totally valid, totally works. I'll just do it in a different order, just so we see that. So I'm going to just start with the conclusion and make it false. Or sorry, make it true. Sorry. Yeah, sorry, no, make it false. But is it clear why this would show it's invalid, right? If I can make the premise is true, but the conclusion is false, then the premises do not imply the conclusion. So to make the conclusion false, that's easy, right? I set, so make not R false. So that's the same as R is true. Okay. So let's just, or instead of saying make, maybe let's say suppose. Suppose not R is false. Now, if you think about it, how am I going to make the premises true? So Q is easy to make true. So this settles, like, now the conclusion is false. So, okay, I want to make Q true because I need my premises to be true. How am I going to make this premise? Well, which one should we do next? So not R is false. Actually, not R is false. So this one's automatically true. We don't need to do anything to make that one true, right? Because if you have an implication and the first part is true, is false, then the whole implication becomes true, right? That's something to memorize. So actually, I'm going to kind of ignore this one. It's going to be true anyway. And I'll look at this one, and Q is true, so not Q is false. So I need P to be false, because if P is true, if you have an implication, true implies false, that's false. So I need this one to be, I need P to be false. So P is false. So now, so just with this stuff, well, and the fact that R is true, this means that the premises are all true. So the argument is invalid. Okay. So P false, Q true, R true. So just a bit of terminology. I would call this a counterexample. To the argument, or just counterexample. So, because this is an example which shows that the argument is not valid. Any questions about that? Okay. Okay, so that's just like one example of how to show something is not valid. It'd also be nice to be able to show things are valid, right? And to come up with valid arguments and to kind of verify them. So basically, to show that an argument is valid, the method is kind of similar to what we were doing with the laws of logic. Remember with the laws of logic that we did earlier today? So you kind of start on one side and you want to get to the other side using logical equivalences at every step. Here, what you want to do to show that an argument is valid, you want to start with your premises, or yeah, in some sense you start with your premises, you apply a bunch of either logical equivalences or logical implications, and you derive the conclusion. So you want to start at the premises and get to the conclusion using these or those, right? Logical equivalences or logical implications. So you kind of so you start with the premises and derive the conclusion using kind of known logical equivalences and logical implications, which we call, so, or maybe I'll say known. So we're going to call these, sometimes these get called, I guess in the notes, inference rules. Okay. So it's okay. It's not completely clear what I mean by this. By like start with your premises and get to the conclusion. It'll become clear, I think, when we do an example. But yeah. But first, before we can do any example, I need to actually give you some of these inference rules that we can use. But is the kind of concept clear about what you want to do? Okay. So I'm going to give you even more things to memorize now. Sorry about that, but so here's the first inference rule. Something called modus ponens. Believe it or not, I don't know what that means. It's something in Latin, but it says that, and it's kind of straightforward, I think. So P implies Q, and P logically implies Q. Because if you think about it, if you know that P is true, and you know that P implies Q, then by definition of implication, Q is true. So in other words, if you ever have a situation, like when you're doing this kind of derivation thing, where you have a line of your thing which says that this is true, and you have another line that says this is true, then you can say, by modus ponens, because this is true and this is true, I know this is true. Okay, so that's how you kind of use this. It's kind of combining this fact and this fact, that P implies Q and P is true, to get Q is true. Another one, which we call the chain rule, is if I know that P implies Q and Q implies R, any guesses what that's going to tell me? It's kind of like dominoes. I don't know. If P implies Q and Q implies R, almost. So almost, because if I then told you P is true, then it would be R is true. But this sort of, this doesn't tell you that R is true necessarily, because P might not be true. But yeah, exactly. It tells you that P implies R. Yeah. But if somehow actually the way you're going to use this a lot is you're going to have the chain rule, and then you're going to have a modus ponens thing. And these two things together would give you like that R is true, kind of. So like, yeah. Because often you're going to have two implications. You're going to put them together with the chain rule. And then you're going to see, oh, on another line of your argument that P is true. And then it's going to give you R is true. That's how you usually use it that way. But yeah.
If you were to be like simplifying a question and you saw something like P implies Q and Q implies R, could you just rewrite that as P implies R?
Yeah. So basically, the way we're going to do this is there's going to be kind of like a series of lines, and where everything on the line is either a premise or something that follows from a premise. If some line had this on it and some line had this on it, you could write your next line with this. So that's how you would use it, yeah. Any other questions? Okay. I think I need another one. Let me give you a couple of more. So, so this is kind of an obvious one. I think we might have done an example like this before. So, conjunctive simplification. Conjunction, remember that means and, I think. Basically, it's almost silly, right? But this is P and Q implies P because it implies both of them. But yeah. Disjunctive amplification is kind of the opposite, but with or. So P implies P or Q. And I believe there's possibly several more of these in the notes. I think these are probably the key ones to remember, but there may be other ones that come up as well. But okay, we've done a lot of talking about these things. Let's actually use them. But first, are there any questions about any of these? Okay, let's see. So I've been talking about, at a high level, about how to do these things, writing things line by line. Let's actually see how you would do it in practice. And this is another thing which really you just need to get a lot of practice at. Although it's really similar to the logical equivalence thing. I mean, it's really, really similar to logical equivalence, except the thing is, now instead of just using equivalences, what we can use is also implications. But it's kind of, otherwise it's the same thing. So the question could say, use inference rules and known logical equivalences to show the following argument is valid. So I take not P if and only if Q, not Q implies R, P, therefore R. Okay. It's like hieroglyphics or something. I mean, it just seems like such nonsense, but yeah, we're going to prove that this is true. One thing that's hard about these questions is knowing where to start. I mean, I guess you can always, if you really want to, you can always start with the first premise and deal with it. It's not always clear what you want to do with it, though. So if I was doing this, which I kind of am, but I would probably think about where this is going before getting into it. So like, morally speaking, why is this true? So if P is true, I mean, this is kind of the simplest line. So if P is true, that would tell me not P is false. That would tell me that Q is false. That would tell me that not Q is true. And so R is true. And it sort of makes sense if you kind of go through it in this kind of pinball bouncing around way, you can kind of figure out that, yeah, this is valid. Yeah, I mean, if I was not doing this if we weren't doing this for marks or something, that would be good enough for me. Like, yeah, this, that's false, that's false, that's true, that must be true. I would just do that, but, we've got to prove this using our rules. So, but kind of the key thing is, I guess, that, well, let's see what happens. So I'm going to start with the first premise. So for whatever reason, in the notes, you'll see that they number the lines. So I would number the lines. So I start by writing this. And my reason that I can write this is because it's a premise. So you always have to write a reason. So line 2, I'm going to do this. I'm going to take my premise, and I'm going to split it up. And I'm going to say that this is a known logical equivalence, and I'm also using line 1. So I guess that's why they numbered the lines, so that you can refer back to an earlier line. So my reason that I can write this is because of 1 and a known logical equivalence. Actually, I should say that there's a difference between this and the laws of logic problems. So I gave you the advice for law of logic things that you should turn it into ands and ors and nots. I would actually say don't do that here, because this chain rule and modus ponens are super useful. So, and they involve implication. So I wouldn't actually always turn this. So if this was a law of logic problem, I would turn this into ors. But this is not a law of logic problem. It's one of these valid argument problems. So I would actually keep the implications. I like implications for this. So that's one kind of difference here, because these rules are so kind of powerful and useful. So what I'm going to do is I'm going to throw away half of this. I'm going to just keep this side, that Q implies not P. So which I can do because of, so by 2 and conjunctive simplification. That might seem like a random choice. Why did I do that? The reason I did that is because that's actually, when I did this kind of thinking about this argument, starting with P being true, not P is false, Q is false, Q is true, R is true. I only used one direction. I only used that direction. Well, or sorry, it's kind of this implication that I used to get that. I don't actually need the other one. So that's why I get rid of it. Get a lot of practice with these, because these are tricky. Now what I'm going to do is this. Why can I do that? Yep, exactly. Yep. So what I'm using to get this is I'm using 3, right? And I'm using the kind of contrapositive. So remember, what's a contrapositive of an implication? You switch it, and you negate both sides. Totally. Oh, yes. Why? Yeah, exactly. Where should I write this? Well, okay, I can erase this. Exactly. So we've got our friend, the chain rule, super useful. So I can write P implies R using, I I guess I'm using this premise. I'm using, maybe, okay, actually, yeah. The way that I think we want to do this is we want to write a line which is the premise. So let's do one extra step. I'll just write not Q implies R. The reason is that that's a premise. And then the next thing, which is, I mean, this was not a very interesting step. The next interesting step then is to do P, or sorry, did I mess this up? Yeah, sorry. This should be not Q. I'm writing down this premise, right? Not Q implies R. So now I can say that P implies R because of line 4, line 5, and the chain rule. Okay, another boring line. I just write P, premise, and then 8 is where things get exciting because I can write R. And what's my reason? Yep. Line 6. I'll throw in line 7 as well. And we want to always kind of say some sort of something in words as well. So do you have any thoughts about that? Yeah, totally. So that's from 6, 7, and modus ponens. You might want to just, I mean, MP is good enough. If you just write MP, modus ponens, that's good enough. So remember, an argument is a statement of the form, basically it's like you have premises P1 up to Pn, and an argument is a statement that looks like, P1 and P2 up to Pn. So if all the premises are true, in other words, then the conclusion is true, right? I think we only went through maybe one example of how to show that an argument is valid. So remember, an argument is valid. So when I say it, I mean the argument is valid if it is a tautology right? And it's invalid otherwise. Okay, let me give you one more, or maybe two more kind of methods for showing that an argument is valid or invalid, and we'll do an example, and then actually we'll be done with chapter 1 and move on to chapter 2. Okay, so here's one basic way of showing, well, it's a basic way generally of showing something is true. So something called proof by contradiction. So the basic idea of proof by contradiction is that one way, so I'm going to kind of say this informally, but then we'll do an example and see kind of what it means. But one way to say that, so one way to prove, let's say, that a statement Q is true is to show that not Q logically implies a contradiction. In other words, when I say, so this is just kind of saying in words, you know, right? Remember, we know what not Q is. Remember, this logically implies symbol means, well, that this implies that it's a tautology, and this is a contradiction. So 0, this is like a bold 0, right? So if whenever I assume that Q is false, it leads to a contradiction, then there's no way that Q could have been true, right? Because is that kind of clear? So yeah, so in other words, yeah, one way to show that Q is true is to say, okay, what if I assume it's false? And then you do some logical deductions. You use maybe some logical equivalences and logical implications. And if at the end, by assuming not Q, if at the end you can eventually get a contradiction, you get something, it implies a contradiction, then Q must have been true because contradictions are always false. Okay, so we'll see an example of this in a second. Let me just mention another kind of proof method from the notes, which is called proof by cases. So basically, proof by cases says, well, maybe I'll write it in symbols, that if P implies R and Q also implies R, well, then that logically implies that P or Q implies R. So kind of in words, what this is saying is, like, suppose it's the case that if I assume P is true, then I get that R is true. And if I assume Q is true, then I get that R is true. Then it must be the case if I assume P or Q is true, meaning assuming at least one of them is true, that's going to give me that R is true. Okay. I would say that this is most powerful when Q is the statement not P, right? Because so in that case, what it says is that if P leads to R, if P implies R, and not P implies R, then P or not P implies R. But what's P or not P? Well, yeah, exactly. So P or not P is a tautology. It's always true. So that kind of tells you that a tautology implies R, which actually, if you think about it, if a tautology implies R, okay, well, actually, we can write this using our known logical equivalence. So a tautology implying R is the same as not the tautology or R, which implies R. Okay. This is like maybe not, super important to memorize, but basically the idea is if P implies R, so basically if I assume P is true, it gives me R, and if assuming P is false also gives me R. So in other words, if not P also implies R, then R has just got to be true, right? Because either P or not P is true, and in either case, we get that R is true. Okay, but anyway, these are just some things you can apply in these proofs. Any questions about this? So there's an example of this in so section, I think it's 1.13. Or sorry, not so much of this, but more of the example. Okay. I don't think that proof by cases is something that's going to come up a lot in exams and things like that, but it's something that you should kind of be aware of. Okay. So let's do an example involving proof by contradiction. Which I've just covered up, I realize, but okay, so let's say so the question could say use proof by contradiction to show that the following argument is valid. So the argument is B implies C, C implies not A, therefore A and not B. So right. Or in other words, if you wanted to, yeah. In other words, it's the same as B implies C, right? So the premises are these three things, right? Right. Or, yeah. Okay. So to show that this argument is valid, I want to show that this statement is a tautology, right? Okay, what does proof by contradiction say? So it says, to show something is true, it's the same as assuming it's false and showing that that gives you a contradiction. So to show that this statement is always true, by contradiction, what you would do is you assume it's false and then keep kind of working through it to try to get a contradiction. So here's my question. What does it mean for this statement to be false? Yeah, exactly, yeah. So that's just reminding you of how implications work, right? There's a big, so there's like all these brackets, but the main thing is an implication. So yeah, assuming this statement is false means that we assume the premise, we assume all three premises here are true, and that the conclusion is false. And we want to turn that into a contradiction. So just a kind of side note of what we're going, the approach is we assume, that these three things are true, and that A and not B is false, and try to get right, a contradiction. Okay, so here's how I would suggest kind of formally doing this. Remember, we have these kind of line-by-line arguments. So I would say your first line, so line 1, you should just write, we need to not forget to take the conclusion to be false. So let's do that first. So let's just write that we're assuming not A and not B. And our reason is that this is the negation of the conclusion, basically for proof by contradiction. Okay. For the second line, what I'm going to do is apply De Morgan's law to this. So what do I get if I do that? So I want to say, my second line, I'm going to say 1 and De Morgan, but yeah, yep. Right, so exactly. So the kind of, the not goes inside and it switches the or to the and to an or. So exactly, so not A or B. Okay. So in these things where you're showing an argument is valid, I sort of mentioned this last time, but I want to reiterate this, that implications are your friend. So implications are really useful. So actually what I'm going to do with this, I'm going to turn this into an implication because implications are useful. And this actually has the form of an implication because, remember, P implies Q is the same as not P or Q. So kind of using that backwards, we can say that this is the same as A implies B. So by 2 and a known logical equivalence. Right? A implies B is the same as not A or B. Okay. And now remember there's this thing called the chain rule. So the chain rule is pretty useful here. And we can see actually there's a good setup for a chain rule because we've got A implies B, B implies C, C implies not A, which are sort of, you've kind of got these dominoes set up. So let's put them all together. So maybe I'll do that step by step. So fourth line, okay, fourth line I'll just write B implies C, and I'll say that's a premise, because it is. And now I'll put these two things together. So these things get a bit long, to be honest, but hopefully the kind of procedure is sort of clear. So right, this is by the chain rule. Well, so this is by 3 and 4 and the chain rule. Okay. Chain rule, remember it says if I've got A implies B, B implies C, that implies, or logically implies A implies C. I'm going to now do that again using this one. So I'll say C implies not A because that's a premise. And then I'll put these two things together. A implies not A, which looks like a kind of contradictory sort of thing, almost. So this is 5, 6, chain rule. And then my final kind of nail in the coffin here is I've got A as a premise. Okay. Okay, I want to put these two things together in some sense. What's the rule I can use to do that? I'm not sure. I'm not sure if my question makes sense, but I want to sort of say, here I've got an implication, here I've got the first part of the implication being true. How do I put that together to get the conclusion? So, okay, there's this rule which is hard to remember the name of. Do you remember modus ponens? So that's what I want to use. I want to use 7 and 8 and modus ponens, which will tell me not A. Because it says, yeah, I've got an implication, I've got the first part of the implication, therefore the second part is also true. That's how modus ponens works. And now I've got something ridiculous, right? I've got, if I take, I've got A and not A by 8 and 9. And for this, maybe I'll just write I'll write a known Li, Li meaning logical implication. So all I'm using here is if I know A and not A, then I know the statement A and not A. Okay. Now I'll write 11, and I'll just write, my contradiction, my bold 0 by 10, and a known contradiction. Okay. And that actually completes the proof because remember what was my goal? My goal was to assume that the statement's false and show that that implies a contradiction. Therefore, I know that the statement must have been true. So it's a tautology. And so this argument is valid.